All right, so as you can see, when I made what am I talking about? When I made this note, it starts with the idea that we'd be looking at this fish tank here. So I'm going to do some beautiful art, because that's just what I'm like. Try not to be intimidated. Okay, there's my tank. And the thing we observe is that we can see our little guy right here, and we kind of see him there, and we can kind of see him from the top down here. All right, so when we look at the fish tank head on, we just see the weird phrenology model. But when we look from an angle, we see him from multiple perspectives all at once. So what's going on here? It means that the path light is following must be changing. And we said that light only travels in straight lines. So is that a lie? No. Light slows down or speeds up as it moves from one medium to another. By the way, when I say medium, do you know what I mean? Any artists in the room? When you talk about a medium, what's that mean? Yes, it's a thing, and that was a very good description. Yeah, I mean, you're not wrong. Specifically, when we say it's a thing, what do we mean? You can see describing this stuff is tricky, right? I would say specifically that it is just what you work on, right? And what you work with. I work with oil paints on canvas, right? I work with acrylic paints on birch, whatever. So medium in this case just refers to the material light is traveling through. So when light is traveling through outer space, there's essentially no medium. It's just moving in a vacuum. In this room, the light mostly moves through the air. But let's think about a single ray of light getting to my buddy here. It has to leave, it gets produced in these halogen bulbs, right? It has to go through the thin glass of the bulb. And then there's some air. And then it has to go through this plastic grating. Then there's some more air. Then it has to go through some glass. Then it may or may not go through the air on the other side of the glass and into the water, or directly through the water. Then it has to hit my buddy. It has to bounce off of him, go back through the water, back through the glass, back through the air, through the lens of your eye, which is protein-based, through the fluid in your eye, which is water-based, and strike your retina. Does that make sense? all the way through that path, light is going from one medium to another. And each time it does that, light slows down or speeds up. And it also changes direction. Would you mind getting coffee with wine and just like a quick table? How you doing? How's your weekend? All right. Good. So while you write that, I'm going to start drawing a little ray diagram of this. And what we can imagine is that we have got a fish tank here. And we've got the little object there. And then let's imagine that I am looking at this, not from straight on, but at a bit of an angle. So here I am looking. Now, what it means is that, and I'm not going to do this accurately yet. Does that make sense? We'll get there. But what it means is that the light from the top of this guy's, oh, not what I was looking for. It means that at that boundary, there's a change in direction. The result of which is an optical illusion. Where do I see the object? Well, I see it down there. Does that make sense? All right, and just a note, this one is done just with made-up angles as an idea. Does that make sense? We'll get to the actual angles in a minute, but the thing I want you to note right now is that as far as my eye is concerned, the object is this orange one down here. Does that make sense? Your eye and your brain communicate in such a way that your eye assumes that light has traveled a straight line, and that's where it tells your brain to draw an image and where something is. It's not calibrated to account for light changing direction when it goes from one medium to another, which means that when I look over here, my eyes tell me that this thing is straight in front of me in that line, but that it's also straight in front of me in that line because of this bending effect. And there's one reflection, so it also tells me it's back there. And without some kind of context to figure out which one is the real one, or if any of them is the real one, or where the real thing really is, I have no way of knowing which is which. Does that make sense? All right. No, no. Mine is just for, I should have shown you what it is. It's just a trig table. It just looks like this. Which one did I send you to?
I want to copy one.
I think it's on copier 2. I'm sorry. Now I can tell you who that is.
Is this a questions? Yes, science.
And rates of reactions. Chemical formula. That's got to be Bainbridge. Rates of reactions. What? Oh my God. Check with a last check. Could be a last check. Interesting. Our eyes and brains assume light travels in a straight line. This is the same way mirrors trick us. That should be a star, not a quotation mark. We see the object below its actual location. In this example. Of course, we're only able to see anything because we have a material in our eye called a lens, which takes the light all around us and bends it so that it ends up in one spot, specifically the back of your eye, the retina of your eye, where we can form an image. So our eyes are tricked by this while simultaneously being made using this technology. And your eyes really are, a piece of biotechnology. Does that make sense as a concept? Be okay with that as an idea? Mine your way. Would you tell me if I were? Good. Yeah.
With your eyes having a lens, something like glasses, they need a lens to correct the lens.
Yeah. Yeah, literally, if you need glasses, it's because the lens in your eye is focusing light in the wrong spot. Either in front of your retina, in which case you need a lens on your glasses to just slide that image back a wee bit so it hits your retina, or it's trying to focus behind your retina, and you need a lens to bring that forward. In fact, one of the labs we're doing with this kit right here shows you that. It shows you how glasses fix the lens of your eye. Which, for the record, a camera lens usually has anywhere from 2 to 12 actual pieces of glass in it that work together to get you a better, crisper image. And one that can adjust focus, right? Because keep in mind, the other thing is the lens of your eye doesn't just have to get an image in focus, it has to get different images in focus. Your lens has to be able to change shape so that it can focus on something near you, and then change shape again so it can focus on something far away. It does it all the time in real time without us really thinking about it. But it's actually compressing. Thank you so much. Yeah, of course, yeah, absolutely. All right, so what's happening here? Well, here are some examples. I said the fish because originally I had a little ceramic fish I was bringing in, but I left him at home. So, the weird phrenology head. So there you go. Why does light bend when it leaves water? It's actually a really tricky question. Tomorrow I'm going to show you a little video where somebody much smarter than I explains it to you. The actual explanation requires you to have a level of knowledge of physics that we just don't, right? It's not immediately obvious that slowing down should mean changing direction, right? Right? You can slow down without changing direction, except to say, and this is only an analogy, but think of it as one. Imagine someone was going to push back on me as I was moving. So if I'm moving at a certain speed and all of a sudden somebody pushes back at me, I'm going to slow down. Does that make sense? You ever walked through water before, right, in a swimming pool? You go a lot slower, right, because all of a sudden you have to push against more. This couldn't happen because this isn't how water works. But imagine if there was a wall of water in front of me and I was moving at this speed. When I hit the wall of water, what's going to happen to me? I'm going to slow down. Does that make sense? Because it's going to be harder to walk through. Now imagine that there's a wall of water there and I don't walk into it straight, but I walk into it at an angle. It's going to slow me down. And again, this is an analogy and only an analogy, but you can imagine that like this shoulder would hit first, which would kind of get pushed back, and it wouldn't just slow me down, but it would slow me down and change my direction as well. Does that make sense? And again, electrons don't have mass, they don't have shape, so I'm using this only as an analogy, except to say that when it moves into something straight on, it slows down and just slows down. But when it moves and hits at an angle, it slows down, but it also changes direction. That change in its speed also causes a change in its direction related to the angle of impact. Again, I'll show a video tomorrow that I think does a really nice job sort of taking the actual physics and making it digestible. But all we'll say right now, with a 0 degree impact, it slows down but stays straight. For any change in medium at an angle, and what letter do we use to signify angles? Theta. And here we just use 1 and 2s. I used an I out of habit because we use theta I for talking about reflection, right? But here we just use 1 and 2. The angle it's traveling in the first medium, the angle it travels in the second. If you look here, you can see that when the light is going in this glass block, it goes at an angle, and when it leaves and goes to the air, it suddenly changes angle, changes direction. The denser the medium, the bigger the effect. When we go from air into glass, we get a big change in direction because glass and air have very different optical densities. Whereas when we go from water to glass, the effect is less so. If you look here, it is easier to see the beaker, inside the beaker, where there's air there than where there's water, right? Can we all see that? That from glass to air to glass is dramatic change to dramatic change. Whereas from air to glass is a big change, to water is a small change, to the glass is a small change, to the water again is a small change, to the glass again is a small change, and then to the air is a big change. So the change going from the air into the glass and water is so much bigger than from the one piece of water to the other piece of glass. Does that make sense? So you can much easier see that there is a second beaker when looking through the air portion of this than the water portion. Does that make sense? And the example I use all the time, if you find things that are very similar optical densities, it's very hard indeed to see the light bending. So you know I love this example, but there's a second beaker in this, just like there's a second beaker in that one. and it is all but invisible. You really have to get close and really look at it to see it. It almost looks like a special effect. It always blows my mind just how challenging it is to see that. Even look from above, and you can definitely see it, but it just almost doesn't quite look like it's there. And above and look above. Yeah. Right, definitely there, definitely can be seen. And if I really sat around and played with mixing oils until I nailed the optical density just right, you could really make it completely disappear. It's pretty subtle, right? Like it is not immediately easy to see. Let's see the second one in there. See the second guy in there. Now take a look above. Yeah, so, a good magic trick. You can do that one at home if you have some Pyrex dishes. Interestingly, these are Pyrex, which is a type of glass, borosilicate glass. It's glass that's had boron atoms embedded in it. If you do this with just regular glass or tempered glass, that's the stuff a drinking glass might be made of, it doesn't work quite as well. Much more obvious that's in there because borosilicate glass has a different optical density than just glass that's just made from silica. So, as it happens, we can predict how much the light will slow down. And we call this its index of refraction. So this little formula here tells you the index of refraction. And that gives us a word that we haven't seen yet. Refraction. Refraction refers to light slowing down and bending. This whole process here is called refraction. So the index of refraction just tells you the ratio of light speed in a vacuum, which is what C is. This is the speed of light with nothing slowing it down. And V is the speed of light in that medium. Don't let this stress you out. The important part is this. We'll do some math with this, but basically this tells you how much light is slowing down when it hits something. Does that make sense? If something has an index of refraction of like 1.001, it means light's barely slowing down at all. You don't have to divide its speed by much of anything to get its new speed. Does that make sense? On the other hand, if light slows down and its index of refraction is like 8, that means light is slowing down to be 8 times slower than it normally is. It's slowing down a lot. Does that make sense? The bigger this number, the denser the medium, the bigger the optical effect. Does that make sense? Air does slow light down, but it barely slows light down. Light in air is almost as moving as fast as it moves through space. Not quite as fast. Whereas water slows light down more. It's going to have a bigger index of refraction. Yeah?
Is there any way for the index of refraction to be below 1?
To speed light up? No. By definition, what we call the speed of light is really the speed of anything that has absolutely no interference. 3 million meters per second is the cosmic speed limit, the universal speed limit. It is as fast as anything can go because, and again, this is a level of physics beyond what we are going to be studying in this course, you are constantly hurtling through both space and time. And as you do so, you're interacting with mass, with other objects that slow you down in space, but there's like this fine balance between the two. And in the universe, all of that has to add up to that 300,000 meters every second, which means that if you have mass interactions with things, gravimetric interactions with things, that has to slow you down. That energy has to come from somewhere. If you have, if you bounce into something, that has to come from that. But that is the single fastest speed anything, including information, including waves, including particles, can move in the universe. That's kind of the basic foundation of physics. Again, this is what's called the quantum model of physics, and we'll start to dip our toes into the quantum model of physics in grade 12 chemistry and grade 12 physics, and that's really a more advanced field of study. It's complicated. But yeah, at its most basic, there's this weird phenomenon in our universe that nobody really understands, but you can go faster, you can go faster, you can go faster, and then all of a sudden there's a speed that it's not like, oh, we aren't able to go faster than that, but rather there's no such thing as going faster than that. That is as fast as something can move in our universe. Which also means, for example, that there are stars in this universe that we know are so far away from us, the light will never reach us because we're moving away from them faster than the speed of light. And so there's stars out there that we can never see and never get to. They exist, they're real, they're out there, but they are completely unobservable to us. There's no way to traverse that distance. Period. Interesting. Yeah. Okay, listen. Let me slow down. Here's the weird thing. And this is, don't try to think about this because you'll take a whole course on this. Let's say I threw a light bulb really fast. Let's say I threw it half the speed of light. Shouldn't the light it shines be coming at me at 1.5 times the speed of light? And here's the weird thing. No. And this is where it all gets weird. From your perspective, the light coming at you is still going at the speed of light. From the light bulb's perspective, the light is still coming at you at the speed of light. And the way the universe handles this, and we know this is true, it's been shown time and time again, is that the only way to make that mathematically work is that we actually travel through time at different rates. Yeah, so what happens is that light bulb is shining light, and that light's leaving it at the speed of light. You're standing there, that light is coming at you at the speed of light, but you are moving through time faster than the bulb, so that by the time the bulb has moved towards you, it is younger than you are. We know this, by the way. We have actually sent twin atomic clocks, left one on Earth and put one in orbit, where it moves faster. An atomic clock is so accurate that it will not lose a millisecond over a billion years. It's pretty good, right? We send one into orbit, we leave one on Earth, we bring it back. The one that went up into orbit is behind the one we left here. Because it moved faster through space, it had to move slower through time. Completely trippy. This is the twin paradox. If your twin left on a rocket and, went 85% of the speed of light to our nearest star and back, a trip that would take him, from his perspective, a couple of years, because he was going so fast, you would have maybe grown 20 years older here, or maybe 50, or if he got really close to the speed of light, maybe thousands of years and you're long dead, and he gets back and the only person left is me in a jar with my robot spider legs, because you're all just out of here, man. Yeah. Yeah, Interstellar actually handles that, in a very mathematically accurate way. They hired someone and did the work for sure, because they mostly get it. They cheat a bit, but they mostly get it. But yeah, long story short, light only ever travels at one speed, and when it looks like it's changing speeds, what's really happening is it's traveling through time at a different rate than we are, which is weird. Yeah. Well, I mean, you're time traveling right now. No, and I'm not so the weird thing you have to understand is that yes, time travel is real, but it doesn't mean you can just do anything. What it means is that all the math on our universe tells us that time and space aren't different things, they're part of the same thing. That at all times we are traveling through space and time. And there's a trade-off between those. Really just Pythagorean theorem math, which is the faster you move through space, the slower you move through time, and the slower you move through space, the faster you move in time. we aren't aware of anything that lets you move in a reverse direction in time, so you can move faster or slower forward in time. But again, like, if you want to meet your great-great-grandkids, just get yourself on a rocket that's moving really fast, close to the speed of light, take a trip on it, come back, and you will have moved through time much slower than everyone else here on Earth, and you can meet your grandkids or your great-great-grandkids or, 2 billion years from now. Spoiler alert, it's not going to look hot. Sun will be like busy starting to envelop. Well, not 2 billion, 4 billion years. Don't go too far is what I'm saying. But we aren't aware of currently any mechanism that lets us move backwards through time. And I am not a quantum physicist, and I can't speak to the feasibility of that. I took like 2 quantum mechanics courses, so I know just enough to be dangerous. All right. So let's take a look at this. Again, the important thing here is not to get too much into this math, though we'll get to that. But let's take a look. In a vacuum, light has an index of exactly 1, which means in a vacuum, light doesn't slow down at all. On the other hand, in diamond, light slows down and bends a lot. And everything here is somewhere in the middle. So you can see air slows down light, bends light. Carbon dioxide gas does more. Water, substantially more. Alcohol, more than water. Glycerol, more than alcohol. Carbon disulfide, more. And you get down to crown glass, flint glass, ruby, zircon, diamond, all these things. Every material that's transparent has an index of refraction. It slows light down some amount. Does that make sense? We can do some simple math with this. What speed does light travel in a ruby? Well, it's actually pretty easy. We know that N is equal to C over V. If I want to know the velocity of light in this, what can I do? And so many fraction equations in this course. Do you hate fractions yet? Yeah? Yeah, we rearrange it. How could I solve for V here? Yeah, I'm going to have to multiply both sides by V so we can get it out of the bottom of that fraction. So I would have Vn equals C. And of course, V is still what I want to solve for. What would I do from there? Yeah.
Divide both sides by n.
Divide both sides by n. And so my equation that I can work with is V equals C over N. And again, listen, I want you guys to start getting comfortable with algebra, but this isn't an algebra course. If you knew the equation and needed help with the algebra, I'd help you. Does that make sense? Okay, and then we can actually put numbers in here because we know C. What is the speed of light? Yeah, 3 million meters per second, right? Which I can say as 3 times 10 to the 9. If you want to write 3 million, that's cool. So that is a constant. This we know. And what about the N of, what is this, ruby? Do we know the N of ruby? Yeah, we know that ruby slows light down by 54%, has an index of refraction of 1.54. And then you can just plug that into your calculator, and I can do it for us. Sorry? Did I screw up?
I wonder if you put down for scientific notation to the power of 9 or 7.
Oh, I'm sorry. Yeah, it's 9. And so I could go to Desmos, which is my favorite calculator. And I could say C equals 3 times 10 to the exponent 9. And I could say N of ruby is equal to 1.54. And then I could just say V equals C over N of ruby. I could also just punch the numbers in, but it makes me happy to do it this way. I feel very fancy. I feel like a fancy boy. And what do we get as our speed? 1.94, 1.95 times 10 to the 9. In other words, when light goes through a ruby, it's only going about 2/3 of its usual speed. That's a serious slowdown, right? 1.94 times 10 to the 9 meters per second. Now, is this a calculation we're going to spend a ton of time doing often and often? No, we don't really care about it, but it's interesting to know. By the way, we now have detectors that are sensitive enough to, detect the speed of light just by actually seeing the speed of light. We have a very sophisticated device now. These numbers can actually be gotten experimentally just by testing them. That's where they come from. Does that make sense? It's not some theoretical number. Another question. When light travels through an unknown material, it slows to 156,250 kilometers every second. What is the material? How could I figure that out? I want to know which of these materials slows light down to 156,250 kilometers a second. What could I do? Yeah.
Well, you have given C and B.
Yeah, very good. What we know is we always know C. In this case, what unit are we working with? Kilometers a second. So do we know C in kilometers a second? Light goes how many kilometers every second? 300,000 for kilometers a second. By the way, you'll never have to have that memorized. All right? It'll always be written down for you. You probably will memorize it, but you don't have to. And we know V in this case, which is what? (156,250 kilometers a second). And we could find what the index of this thing is. Because if we find the index, we could then just look at the chart and see which of our materials it is. Does that make sense? How would I set this up? What does n equal? This one mercifully requires no rearrangement. Isn't that nice? What does n equal? Yep. C over V. And we can plug those numbers in. And I'm going to need a calculator here. So I will again grab Desmos really quickly. What do we get as an index when we do that? We get an index of 1.92. And look at the table above. Does that equate to any material? Is it close? Did I screw up the question or are we good?
No.
Hey, look at me. So what is the material? Does that make sense? Now, if it feels like I've rushed through these two questions, that's because I'm not so concerned about this side of this stuff. Does that make sense? I care about it. Like, whatever. It's interesting from a physics perspective, but this is an optics class, so what we really care about is the bending of light, the changing of direction, doing ray tracing.
Excuse the interruption.
Yeah.
Carolina, could you please post your attendance?
Didn't I said I was... yes, absolutely. Oh, I thought about it, and then I didn't, because I had the fish tank, and I got... Man, starting the week off with failure. That's just something we tell children. I'm kidding. I'm kidding. People do grow from their mistakes. Just not me. Smart people grow from their mistakes. Numbskulls, not so much. You have no idea what it's like working with half a brain. And not like the good half either. Alicia's here. Murray is here. Toby is here. Alexander is here. Sierra is not. Shaylin is here. Dylan is here. CJ is here. Mila's not. Isaac is here. Bria's here. Abby's not. Isaiah is here. Kyle is not. Abdul is here. On's here. Taylor's not. Anya is here. Haley is here. Lila is not. Post the attendance. But actually we hit no, which doesn't make any sense to me. There we go. Okay. So this bit of calculating how light speeds up, how it slows down, that's fine. You should be able to work with that. And I hope you see that physics is a lot of find an appropriate equation, rearrange it to solve what you want to solve for, go. If the algebra of that stresses you out, all I can tell you is algebra comes with practice. The more you do it, the easier it gets. I remember feeling like I was particularly bad at it when I was a grade 10 student. And now I don't even think about it, unless it's a tricky one. And then when it's a tricky one, I still figure it out. You still just, the skills develop. And if it's really bad, I just get Calford. That's my secret. You could do the same. And I would say too, that like, when you're a scientist, or I was a science major, I was never a scientist, but I was a science major, it is not uncommon to go talk to other people and work the math out together and get help with the math. Does that make sense? Your primary job isn't to do math, your job is to use math. Okay, now today we're going to introduce the predicting a bending of light. But to do that, I need to introduce you to a topic that unfortunately you haven't seen in math yet. How do we measure angles? In degrees. What's a degree? Oh, yeah, absolutely. What else? In terms of angle, what's a degree? It's weird. What's a degree? Sure. What is one? What's 1 degree? How much is 1 degree? Show me. It's not much, eh? So what is it? Why is that 1 degree? Why isn't this 1 degree? Why isn't that 1 degree? Why isn't this 1 degree? Wouldn't that be nice? Hey, make sure you make a 1 degree triangle. Sure, that's easy. Boom. Like, why is this 1? What's all the way around? 360. Okay, can we pause? Look at me. It's really stupid, right? Like, we all just take for granted that it's 360, but like, what? Why?
Should be 100.
Sure, yeah, or 10, or 2 times pi. Like, whatever, it should be anything, but 360? Why? Why 360? The answer is the Mesopotamians counted by 60s. We count by 10s, right? So we just have 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then when we get to the 11th thing, which is the number 10, we just have to start recycling digits, right? Now it's 1 to 0. We count by 10s. Everything grows by 10s. Decimal system, right? The Mesopotamians had 60. If you're a well-educated Mesopotamian, you had to know 60 different symbols for counting. Now, can we agree? That's got to be complicated. But their number's based on 60, and they got to this stuff way quicker than anybody else, thousands of years ago. And so the stuff hangs on. How many minutes in an hour? 60. How many hours or seconds in a minute? 60. Even 240 divided by 10 hours in a minute comes back to, or in a day comes back to 60. All right? 60 pops up all over math, not because it's a good number to work with. It's not. It's dumb. We count by 10s. We have 10 fingers. Makes counting things easy. Don't have 60 fingers. But that's where it comes from. It's simply a matter of history. Does that make sense? During the French Revolution, when the revolutionaries took over France, they introduced decimal time. 100 seconds in a minute, 100 minutes in an hour, 10 hours in a day. Makes sense when you think about it. When's noon? 5 o'clock. in the middle of the day. Didn't hang on, didn't last. But you can see why it makes sense to come up with something like that, because 60 is a weird number to work with. Angles being measured in 360 degrees is fundamentally ridiculous. And the fact that it makes sense to you is just a sign that you're brilliant. I'm serious. Because you instinctively know what 90 degrees looks like. So I could now tell you, ready? Show me roughly what like 104 degrees looks like. Just guess it. Right? And you can all kind of go, more or less like that. But that's a crazy system, right? 90, 180, 270, 360. It's crazy. Well, modern mathematicians and scientists, and I say modern, I mean this goes back to like, like 1,000 years. But we have a few other ways of expressing angles. And the three most common ones you're going to learn in math this year. So I'm going to hand this out for you. This is what we call a trigonometry table. But you're going to see there are three new ways to express angles that you haven't seen before. You've probably seen these buttons on your calculator before and maybe wondered what they did. Okay, so if you look at this table, you'll see that for every angle measured in a degree between 0 and 90, I've also expressed that angle three different ways. What are the three other ways we have of expressing them? Sine, cosine, and tangent. The sine of an angle, the cosine of an angle, the tangent of an angle is just another way of expressing how big it is. Does that make sense? At first, it may seem counterintuitive, but as you get used to it, it's not that bad. What is sine? Angles between here and here, right, are measured from 0 up to a maximum of 90, right? Can you picture that? The sine, when the angle is 0 degrees, take a look here. What's the sine of that angle? Look at the table. An angle of 0 degrees has a sine of 0. And if we go all the way up to 90, an angle that is 90 degrees has a sine of 1. So if you look, instead of going from 0 to 90, it just goes from 0 to 1. Now, you can't just divide by 90 because it's not a linear relationship. It's a curvy relationship. I can show you what the relationship looks like in Desmos. You've probably seen this graph before. So I'm just... Actually, I'll just make it. Yeah, you've probably heard of a sine wave before, but this is the relationship. That's 0 degrees, that's 90 degrees, and that's how it looks. Does that make sense? We'll talk later on about how this in math class, about where this comes from, how this is arrived at, and why it's useful. But suffice it to say, one of the ways it's useful is that you can do much more, you can calculate with it directly in a way where you're always having to do conversions when working with angles. So in math, whenever we're working with angles, we are going to work with either the sine, the cosine, or the tangent of that angle almost exclusively. You'll learn about radians and gradients later on. Don't worry about it. Let's just make sure we can read this. If an angle was 53 degrees, what would the sine of that angle be? Very good. If you do some math and you get an answer that says a sine of 0.309, what's that angle in more common degrees? Sine is 0.309. Sorry? 18 degrees. Does that make sense? In this course, we're only going to worry about the sine of the angle. Though if you look, cosine is the exact same curve, it just goes in the opposite direction. Does that make sense? Sine and cosine are the exact same thing. They just go in different directions. And the reason we use one or the other, maybe, do you see how this kind of flattens out on the top? It can be hard to tell the difference between these two because that curve flattens. So where we might get a kind of wiggly answer with sine, we would use cosine instead, where they're very different in that range. Does that make sense? And likewise down here, cosine is wiggly. It doesn't change much, which makes it hard to get an accurate reading. So we'd use the sine. For the purpose of this course, we're just going to use the sine for everything we do. Does that make sense? You can use your calculator to get that answer, but I actually think the table is a way better way to look this stuff up. You just physically look at it. We're about to have a bell. That's great, because tomorrow we're going to do our actual trig math. But really quick, hey, before we go, shh, I want you to look one more up on here. Everyone tell me the sine of angle 25 degrees. 2-3, but that's all right. So listen, that basic skill of being able to look at this table and tell what the angle is going to come in really helpful tomorrow when we get doing math, all right? No, it's good. You're going to like it. Can I tell you? Hey, look at me. Tomorrow is by far the easiest equation that we've dealt with. There's no fractions. It's all multiplying. Isn't that nice? You will never have to solve for something on the bottom of a fraction tomorrow. Much easier.